Welcome, Woodstock physics students, to the first in likely a series of instructional tutorials about energy. This first one here, we just want to talk a little bit about the different kinds of energy that we had listed in some brainstorm lists a couple of weeks ago, and maybe to start put some equations with them, some formulas with them, so we can actually calculate different kinds of energy. So you should have this handout that has a list of different kinds of energies. And the first one we want to look at is kinetic energy, the energy of motion. And I want to kind of just highlight here the fact that we're thinking about, in this particular moment, large-scale objects, things like, baseballs or bowling balls or people or cars and so on. And this kinetic energy can be expressed as 1/2 mass times velocity squared. The mass would be in kilograms, which is a little bit of an unusual unit for us in some ways, and the velocity will be in meters per second. All right, so that's a fairly straightforward calculation. Notice that it depends more heavily on velocity than it does on mass, because the velocity gets squared. Also note that it's the translational velocity, so rotation and vibration, those kinds of motions won't be captured by this kind of kinetic energy. Okay. Let's zoom down and think about particles. We've thought about particles quite a bit, and here again, the formula is exactly the same, the thinking is exactly the same, but one can imagine that the masses would be, of course, much, much smaller. So if you're talking about, a proton, it could be 10 to the minus 27th kilograms, whereas, an apple could be, a quarter of a kilogram or something like that. So very, very vastly different scale here, but the kinetic energy formula is exactly the same, and the units are the same, and so there's some comfort there that it's not a different idea at a small scale. So whether we're talking about an oxygen molecule in air, or whether we're talking about a tennis ball being hit by a racket, the formula would be exactly the same. Let's take a quick look at potential energy, gravitational potential energy. There's a lot of different kinds, there are many different kinds of potential energies. The one that's easiest to think about is the potential energy due to gravity. And here we have our mass, again in kilograms, this value g, which we'll talk about in a second, and h, which is the height above the surface. And so let's just add in a little bit of text here, and we'll do that in just a second. Hang on. So just adding in some thoughts here about gravitational potential energy. The h is the height above the surface in meters, and g is, a little typo there, 9.80 meters per second squared. That's at or near the Earth's surface. So we're assuming that this is on the planet Earth. Okay. Elsewhere, the value of g, elsewhere in the universe, in the solar system, the value of g would be different depending upon the local gravitational influence. Okay, so let's just take one last look here at elastic potential energy, and I've written here sort of ELPE, elastic potential energy. That's 1/2 k times x squared, where x is the amount that the spring has been compressed or expanded, and k is the springiness of the spring. A high value of k will mean that the spring is quite springy, and you'll store a lot of energy in the spring by compressing it by a centimeter or so. A low value of k means that not much energy will be will be stored. Okay, so so those are some formulas. We have other kinds of energies which we won't introduce formulas for right now because they're either too complex or too specific to particular outcomes. Okay, let's just pause it here as a first introduction to sort of energies, and we'll pick up with another video at another time. Thanks.